And we're going to use the information that we used with Lewis structures, and we're going to apply it to resonance. We're also going to look at formal charge. We're going to look at bond order, bond length, and bond energy. So we're going to kind of pull everything together here. Okay, so formal charge is a tool that chemists use to try to figure out what's going on with the arrangement of the atoms. And eventually we're going to look at their three-dimensional relationship in space. So like I said, it's important to draw Lewis structures because eventually we're going to talk about how do they apply to the arrangement in space with atoms. Now, the reason why we care about formal charge is we want to figure out what is the most stable and likely structure. And like I said, this is a tool that helps us identify the best structure possible. Now, typically, we're looking at a neutral molecule, and as a result of it, we want to have a formal charge that overall is zero. Um, the other thing is we will use it for polyatomic ions, and when we create polyatomic ions, we need to have an overall charge for that ion, and we'll talk more about that in a minute here. Okay, now, when you're using formal charge, you're trying to make sure that the atoms involved in this covalent molecule have a formal charge that is low enough to create a stable molecule. The other thing that you have to consider is that when we're looking at electronegative atoms, we're going to pick arrangement in space with covalent bonds that um, give the formal charge maybe a slightly more negative charge. And you'll see more when we actually do examples of this. Okay, so what is formal charge? Like I said, formal charge is a tool. Um, and the way chemists use it is they look at the valence electrons and then they subtract the number of electrons that are given in that structure. And the electrons that are given in that structure, they typically count up the number of lone pair of electrons, and then they add the number of bonding electrons divided by 2. And when you do this, it'll just become a second nature with your practice. Okay, so here we have an example of two Lewis structures, and the possibility is either on the left or the right. The question is, they both have an electronegativity of 3.0. So this is a conundrum. We're trying to determine which one's the better structure. So you need to look at each individual structure, and you should be able to list out the valence electrons. So you should know that nitrogen has 5 and chlorine has 7. That should become automatic to you. Now let's look at electrons assigned. Now this nitrogen has 1 covalent bond, so we're only going to count half of the electrons involved in the covalent bond. So it has 1 covalent electron, and it has 3 sets of lone pairs surrounding it. So that's a total of 6. So nitrogen should have 7 electrons assigned to it. Now this chlorine here has 3 covalent bonds, so we only want to count 3 covalent electrons plus 2. So one of these chlorines here should have 5 electrons assigned to it. Now this last chlorine here has 1 covalent bond, and it has 6 lone pair electrons. Should have a total of 7 when you are looking at electrons signed. So notice that we have 7, 7, and 5. So here's the nitrogen, which has 7. This central chlorine has 5, and then the 2 exterior chlorines have 7. And then we need to subtract them. And, oops, sorry. When we subtract them, we have a formal charge of -2 for nitrogen, and then we have a +2 for chlorine. Because they are not close to 0, this structure is probably not going to be favored. Okay, so once again, you should know that chlorine has 7 and nitrogen has 5 valence electrons. Now if we look at this nitrogen here, it has 3 covalent bonds plus 2 lone pair electrons. So there should be a 5 underneath this nitrogen. And you could argue that this chlorine, which is similar to the other two, has one covalent bond, so one electron plus 6 lone pair electrons. So each of these should have 7 underneath it. And sure enough, they do. And then when you subtract, they all have 0. So as a result, this is the more favored Lewis structure. Okay, here we have two sets of polyatomic ions. Notice they have a negative charge overall, so we would need to factor that in when we figure out formal charge. And sulfur and carbon share electronegativity, so the question is which one is going to be the central atom? Okay, so valence electrons, we should have 4, 6, and 5. And sure enough, we do. And then the carbon over here has 2 covalent bonds. So we're going to add 2 plus 4. So carbon will have 6 here. Sulfur has 4 covalent bonds. So there's going to be 4 underneath sulfur. And then nitrogen has 2 covalent bonds plus 2 sets of lone pairs. So this should be 6. So when we do the formal charge, notice that we have a -2, a +2, and then a -1. These formal charges are too varying. They're not as close to 0. So as a result of it, this is not a favored structure. Here is the next structure. So we have 4, 6, and 5 again. All right, so this sulfur has 2 covalent bonds plus 2 sets of lone pairs. So its number should be 6 underneath. Carbon has 4 covalent bonds, so it's going to have 4 electrons assigned to it. This nitrogen has 2 covalent bonds plus 2 sets, so it should have 6 assigned to it. And as a result of it, when you subtract, we have 2 zeros and a -1. Notice that when we add them all up, we still have an overall -1 charge, so that's good. And because these two atoms have a lower formal charge, or it's closer to 0, this is the favored structure. Okay, so here we have an example of a polyatomic ion, and you have to get really good at adding up all the valence electrons. So notice that we have 6 valence electrons for sulfur and oxygen, and we also have an overall -2 charge. When we add up all the valence electrons, notice that we have a total of 32 electrons. So you want to make sure you keep track of all the valence electrons plus the additional electrons due to the polyatomic ion. Okay, so because sulfur and oxygen both have 6 valence electrons, you can't argue one over the other, but you could argue that sulfur is lower in electronegativity, so as a result of it, it's going to be the central atom. Notice that the oxygens are surrounding sulfur. So we want to complete the octets. Remember, we want to keep track of all the valence electrons that we're using. And we're eventually going to go to formal charge to figure out what is the desired structure. So we have all of the electrons being used. And the thing that you have to keep cognizant or be aware of is sulfur is in the 3rd energy level, so it has access to d electrons, so it's possible that it's going to exceed its octet. Now oxygen does not have that. Oxygen is in the 2nd energy level, so you got to be careful it's not going to exceed its octet. Okay, so we're going to look at formal charge, and when we look at formal charge, notice that they start off with 6 valence electrons, and as a result of it, they have access to 7 electrons. And when you look at the formal charge for each oxygen, it ends up being -1. Now, because this molecule has an overall -2 charge, that means that the sulfur has to have a positive charge to balance off all of the negative charges of oxygen. And when you look at that, it has a +2 charge. So when you add up all the formal charges, overall it should be a -2 charge. Now the question is this a valid Lewis structure? If we were to change the way that oxygen shares its electrons with sulfur, notice that we're introducing double bonds. And like I said, sulfur is in the third energy level, so it can exceed its octet. So we need to look at formal charge. And notice that oxygen, when it forms a double bond with sulfur, we're actually bringing its formal charge closer to zero. So we have two oxygens with formal charge of 0. We have two oxygens with a formal charge of -1. We have to have an overall -2 charge with this compound. And because of the number of covalent bonds and the number of valence electrons available to the sulfur, the overall formal charge for sulfur is 0. This actually is lower or closer to 0. So as a result of it, this is probably the more accepted Lewis structure. Okay, so let's talk about bond energy. This is bringing back one of the topics that was earlier in this section here. Please remember that when you have two atoms and they're further apart, their potential energy is higher. When you bring them closer together, they have a lower potential energy. So they have to release energy when they are bonding. So energy is released whenever you're forming a bond, and you could argue when you're trying to break that bond, that's the amount of energy that you have to put into the molecule or the set of atoms. So as atoms move further away from each other, potential energy increases. Okay, now let's talk about resonance structure. For some of you, this might be familiar. Some of you may not be familiar. In order to have resonance, you need to have a molecule that has a double or a triple bond. So if you just have single bonds, you don't need to worry about resonance structure, okay? With resonance, what it means is that you can have more than one possible Lewis structure. So molecules actually, when they have double or triple bonds, they will move their electrons around and share them differently to give them slightly different Lewis structures. Now, when we are talking about resonance, it is so important that you draw two-way arrows around the different types of Lewis structures. If you do not do this, the AP reader will not accept this as a resonance structure. And I'll show you what it looks like here. So here we have ozone, and notice that the compound on the left is almost like a mirror image of the compound on the right, and there is a double-headed arrow that is drawn as a result of it. This is what a resonance structure is going to look like. So you have more than one Lewis structure, and they are sharing a double-headed arrow, and that tells the viewer that this is resonance. Now, notice that when we're looking at bond order, we need to factor in how much bond length is actually being seen by the molecule. Now notice that there's one double bond and there's one single bond. So that's a total of 3 bonds. And if you divide it by the 2 different bonds, you get an average of 1.5. So this structure, or this covalent compound, its average bond length is about 1.5. So this is just to tell you what is the bond length or the bond order of the molecule. Okay, here is an example of a resonance structure. So notice that it's a polyatomic ion, nitrate ion. You once again are going to have to draw using formal charge, and notice that because there's a negative sign here, the overall formal charge on this molecule better be a -1. So you want to have the formal charge of each atom close to 0, and when you add up all the formal charges together, they should equal -1. Now notice that there's a double bond, so there is a possibility of resonance, and because there's 3 sets of oxygen is able to share its electrons in such a way that it moves the double bond around. Okay. Now you could argue that there's a total of 4 bonds and there's 3 sets of them. So when you take 4 divided by 3, the overall bond order is 1.33. Okay. Here is another resonance structure. Now you got to be careful here when you're drawing this resonance structure, and AP is pretty good about giving formulas to you so that you can draw a Lewis structure. Be careful because this hydrogen is in the middle of the formula. It does not mean that the hydrogen should be in the middle of the Lewis structure. I don't know if you remember, but hydrogen is one of those atoms that cannot be in the middle of a molecule. It's typically in the periphery or the exterior of the molecule. So once again, you want to use formal charge and you want to draw the Lewis structure with the lowest number of formal charges for the different atoms. And notice because it's a -1, the overall formal charge should equal number -1 if you add up all the formal charges. Now, this one you have to be a little careful about because the resonance is only happening between the oxygen and the carbon. There should not be any resonance between carbon and hydrogen. So as a result of it, we really only have 3 bonds here that are exhibiting resonance, and we want to divide it by 2 because we have 2 sets of them. And as a result, the bond order, the effective number of bonds, is 1.5. Okay, now we want to compare bonds because we want to see which one has the shortest number of bonds. Now, please be careful here. Please remember, the higher the bond order, the shorter the bond, because you would argue that a triple bond is going to be shorter than a double bond. So we're looking at the bigger number to tell us which one is the shorter bond. So here we have NO2 minus and then we have NO3 minus. And once again, you want to figure out formal charge. You want to make sure that together all these formal charges equal the negative charge of the polyatomic ion. And we're going to argue that there's 2 sets of bonds, but there's a total number of 3 bonds. So 3 divided by 2 gives us a bond order of 1.5. And then here we have a total of 4 bonds, and there's 3 sets. So 4 divided by 3 is a bond order of 1.3. Now, please remember, you want to pick the higher number, not the lower number. So you would argue that NO2 minus has the shorter number of bonds because its effective bond order is 1.5. Okay, so here we have 2 other molecules. Now, these are not ions, so their overall formal charge should add up to be 0. And because there is 1 double bond, 2 divided by 1 is going to give you a bond order of 2. But here on the bottom molecule here, we have 3 bonds and we have 2 sets of them. So 3 divided by 2 gives us 1.5. So as a result of it, the higher number is the one that's going to be the shorter number of bonds. And you would argue that the double bond has the highest bond energy. Okay, there are some problems with Lewis structures. You could argue that a lot of the double bonds are not really double bonds. They're more like 1.5, 1.3, 1.25, and that's because the atom is, or the molecule is really good at sharing electrons and actually making that bond less of a double bond. And I'll show you some exceptions to or problems with the Lewis structure here. Okay, so if you have an odd number of valence electrons, when you add up all the electrons that are given for that molecule, that is where it's hard to have a Lewis structure. So the best example is nitrogen monoxide, so NO. So you have 11 valence electrons, and as a result of it, you would argue that oxygen, because it's more electronegative, it should see more of the electrons. Okay, and notice you have this one unpaired electron, which is a problem because a lot of stable molecules don't want to have an unpaired electron. Okay, so the interesting thing is that oxygen will actually share its electrons with nitrogen. So as a result of it, it will essentially form a double bond. Now you're like, well, what about that unpaired electron? Well, okay, there are some molecules that will have unpaired electrons. Um, they are not the most stable. We tend to call them radicals. I don't think AP expects you to know that, but this is a situation where unfortunately the Lewis structure doesn't really help us to understand the accepted, well-known Lewis structure. Okay, here is another Lewis structure where there's some problems with it. And I told you in the other set of notes that we just accept the fact that boron has an incomplete octet. And over the years, I've seen many chemistry students want to complete the octet for boron. Now, please remember it has a core charge of +3. It has access to 5 protons. It's not highly electronegative. Um, so we are okay with the fact that boron has an incomplete octet. Now, if you try to complete the octet for boron, um, formal charges will show you that it's not a favored structure. Notice that you have a -1 for boron, which it's not the most electronegative, so it's not a good number for it to have as a formal charge. Fluorine doesn't want to share its electrons as much, so it having a +1 formal charge is not accepted either. Okay. In addition to that, the interesting thing is, um, as chemists do research, they actually find that bond length um, between boron and fluorine is shorter than a single bond. And as a result of it, if you were to add up the bond orders for this, you would argue that this structure has a bond order of 1.33. And you could argue resonance based on the fact that there is a double bond here. Now, the other challenge with this is if you were just to subtract the difference in electronegativity between boron and fluorine, you could argue it's 2.0, which is greater than 1.9, and you could argue that this is an ionic compound. And the way this structure has been drawn here, this shows the ionic structure of boron trifluoride, and you could argue that there's an ionic bond that is between boron and fluorine. Now, the interesting thing is that the leftmost drawing that is part of this resonance structure drawing here is the accepted and more dominant um, view of this molecule. So even though you could argue that boron trifluoride has ionic compound or ionic bonding, um, that there's resonance within this molecule, the leftmost compound is the more dominant and accepted form. Okay. The other problem with the Lewis structure model is we assume that when you are drawing Lewis structures, that every atom wants to satisfy the octet role. And obviously, when you're talking about elements that are period 3 or higher, because they have access to their d electrons, they're more likely to exceed their octet. So as a result of it, the Lewis structure is something that we have to think outside the box for these types of molecules. Okay, so we're eventually going to talk about molecular shape and the three-dimensional positions of the atoms with this type of information.